And welcome back. As we continue our cosmic journey, let's go ahead now and take a look at the various orbits in the solar system. So when we start talking about orbits, the path of an object under the influence of gravity through space is called its orbit, whether that object is a spacecraft, a planet, a star, or even a galaxy. An orbit, once it's been determined, allows the future positions of the object to be calculated, so we know exactly where it's going to be at some point in time. Now, 2 points in any orbit in our solar system have been given special names. The place where a planet, for example, is closest to our sun and moves the fastest is called the perihelion of its orbit, and the place where it's farthest away and moves the most slowly is the aphelion. Now, for the moon or a satellite orbiting Earth, the corresponding terms are perigee and apogee. We use the term moon here when we start talking about moon with the lowercase m. This is just referring to a natural object that goes around a planet, and the word satellite to mean a human-made object that revolves around a planet. If you have moon with a capital M, that of course is referring specifically to the moon that is around Earth. Alright, if we take a look at the orbits of the individual planets, this table here is kind of giving a summary of the orbital data for planets. So we have Mercury all the way through Neptune, and we even threw Ceres in here just as a reference for a dwarf planet. And we have in here the semi-major axis given in astronomical units. We have the period of those planets, which is how long it takes to complete one orbit around the sun in years. And we have our eccentricity, or kind of our variance with those orbits. So if you look, for example, Earth has a semi-major axis of 1 at a period of 1.0 years. By comparison, if we look at, let's say, Venus, you'll see that it is 0.6 because it takes 6/10 of the time to complete its orbit in relation to Earth. And of course, as we move through the solar system here, you can see the closer we are to the sun, the shorter that period, and the farther away from the sun, the longer that period. If we look at the semi-major axis, we'll also notice a kind of similar ratio here. All right, for example, Mercury has a semi-major axis of 0.39, whereas if I look at something like Jupiter, you can see I have a semi-major axis of 5.2. Again, we kind of have this ratio of things that's being respected. And we look at our eccentricity values, we have some values here that are pretty close to being less than 0.1, except for Mercury. So that is going to allow us to kind of start thinking about our planets a little bit here as being orbits on a plane. So Newton's work that we previously looked at enables us to calculate and predict the orbits of planets with marvelous precision. According to Kepler's laws, Mercury must have the shortest orbital period, which is actually 88 Earth days. At the opposite extreme, as we just saw on the table, Neptune has a period of 165 years. Now, all the planets have orbits of relatively low eccentricity. Most eccentric, as we saw, was Mercury with 0.21, and the rest of its eccentricity is smaller than 0.1. It's pretty fortunate that, among the rest, Mars has an eccentricity greater than that of many of the other planets. Now, the planetary orbits are also confined close to a common plane, and this is where the eccentricity value starts coming in, which is near the plane of Earth's orbit, which we refer to as the ecliptic. Now, the orbit of the dwarf planet Pluto is inclined about 17 degrees to the ecliptic, and the dwarf planet Eris by about 44 degrees. However, all the major planets, so whether you're looking at Mercury, whether you're looking at Jupiter, they're all going to lie within 10 degrees of the common plane of the solar system. And that's a little bit of that variance that they have when they get to, of course, orbit around the sun. So if we start looking at the orbits of, let's say, asteroids and comets in relation to our planets, because obviously these are still celestial bodies that are part of our solar system, in general, asteroids have orbits with smaller semi-major axes than do comets, because wherever most of asteroids at? Well, most of our asteroids are going to be in the asteroid belts, and so they're between the orbits of Mars and Jupiter. And because they're located there, they're going to be closer than our comets. And one thing to keep in mind with that location of the asteroid belt, the two planets that they're kind of wedged between are so far apart that we actually have some stable orbits of small bodies that can exist in that region of the asteroid belt. So something like Ceres has a pretty stable orbit at where it's located. So this image here kind of shows the orbits of typical comets and asteroids compared with those of the planets. So here we have 3 comets that we are having with red orbits, and we have several asteroids with blue orbits. And you'll notice, of course, if we take a look at this, our comets can have what almost appears to be kind of a more erratic looking orbit in comparison to that of our planets, which of course seem to be, at a view, a little bit more cyclical than what we might have here. So if we have more circular looking orbits here, whereas here they're much more pronounced ellipses, and that's because the comets aren't necessarily following the exact same path. They don't live in that same plane as the planets do. If we look at our asteroids, you can see our asteroids are kind of similar here. They don't necessarily have a one-to-one correspondence, but again, they're following in this region here between Mars and Jupiter.